Dear students, this is the continuation of the previous video. Okay. See this question number 3. The series sigma n is equal to 1 to infinity n factorial multiply n plus 1 factorial divided by 3n factorial. Converge or diverge. Okay. Way to do by ratio test. Okay. What we do by ratio test? Limit n tends to infinity. This is a n plus 1 divided by a n, which means the given term is a n. Okay, so if I want a n plus 1, what I do? I replace n by n plus 1. That's why I am putting here n plus 1 factorial. Here I replace n by n plus 1. So that n plus 1 plus 1, so n plus 2 factorial. Divide by, you see here 3n. So I replace n by n plus 1. So 3n plus 3 factorial. Okay, now this is in the denominator, same an. Okay, so now what you do? You write the reciprocal of this and then you do the simplification. After that, what we are getting finally, limit n tends to infinity, this expression. Okay, now here the degree in the denominator, maximum degree in the denominator is n power 3, so that we divide by n cube, both numerator and denominator, so that here we get limit n tends to infinity, this expression. Okay, now you apply n tends to infinity in numerator and denominator. So what will happen? This will be 0, 0, 0. Here 27 plus 0, 0, 0. So 0 divided by 27 means 0 divided by any number is 0. So that here what I am getting, this value is nothing but 0. This is equal to L. Okay, equal to L. So now L is 0. Okay, 0 means less than 1. Less than 1 means by ratio test, what I can conclude that the series converges absolutely. That's it. Now you see question number 4. The series sigma n equal to 1 to infinity n square plus 2n plus 1 divided by 3 to the power n plus 2 converge or diverge. Okay. Now you do the same procedure what you did in the previous 3 questions, that is an plus 1 by an. First we find, then what we do, you take the limit of this, that is limit n tends to infinity of this modulus value, which is going to 1 over 3, as n tends to infinity, this is 1 over 3. So what is this? This is nothing but equal to L. Okay, so this is less than 1. 1 over 3 is 0.3, less than 1. See, that is here, less than 1, which means this given series is also converge by ratio test. That's it. So this is the way how we have to check convergence by ratio test. What you have to do, you have to write an plus 1, then you write an in the denominator, then you apply the modulus, means we have to find the modulus value of an plus 1 by an, then you apply the limit n tends to infinity, then you check what it's giving. Now here, for example, here the value is 1 over 3. Okay, then you check with that. If L is less than 1, converge. If L is greater than 1, diverge. If L is equal to 1, we cannot write anything, neither converge nor diverge. Okay, so this is the way how we make use of ratio test to check the convergence. Okay, now here what we are going to see, Taylor series. If f of z is analytic at z0, then the series of the analytic function f of z is equal to f of z0 plus f dash of z0 over 1 factorial z minus z0, plus similarly we can write. Okay, j is equal to 0 to infinity if here jth derivative of the function at z0 divided by j factorial multiply z minus z0 whole to the power j. So this is called the Taylor series of the given function f of z around z0, around the point z0. Okay, suppose we put here z0 is 0 in the Taylor series, then the series is called Maclaurin series. Now we will see question number 1. Find Taylor series of the function f of z is equal to 1 over 1 minus z around z0 is equal to I. Okay, So now to write the Taylor series of the given function, what we have to do, we have to find derivatives first. See, this is the given function. I rewrite the function. The function is 1 over 1 minus z. But what I write here, f of z equal to 1 minus z whole to the power minus 1. I write this in the numerator. I write comfortably to find the derivatives first. Okay. So now I am finding 4 derivatives. You see, f dash, double dash, triple dash, fourth derivative of the function. Okay. This you know that. So I write here 4 derivatives of the function. Okay. Now see, to find the Taylor series, we need z0. What is z0 given in the question? Given z0 is equal to I. So now to find the Taylor series, what you have to do? You see, the function value at z0. The derivatives at z0 we have to find. Okay. Now what is our z0 is I. So that now we put here, see, f of z we know that. So from here what I find, see, z0 is I. So you put here for z, put z0. For z0, what is given in the question? I. So you put I here. So f of I, how much? 1 minus I power minus 1. Okay. What is f dash of I? Because we need here f dash of z0. So now what I write here, f dash of I. What is f dash of I? That is 1 minus I whole power minus 2, because this is f dash of z. So here you replace z by I, so that I can write. Okay. So similarly, what I do here, see here, this is second derivative of the function. Here, what is second derivative at I? Yes, this. Third derivative at I. Here I am finding. Okay. Now, what is fourth derivative? Fourth derivative here, we know that this, but fourth derivative at I, yes, I found this. Okay. So now, what is Taylor series? This is Taylor series of the given function is equal to f of z0 plus f dash of z0 by 1 factorial z minus z0 plus and so on. Okay. Now, we know every value. Okay. Of the function at I and the derivatives at I. We know that. So just you replace it here. You replace it here. Okay. So now f of z is equal to, see what is this? This is nothing but f of z at I. Okay. What is f of z at I? That is here 1 minus I whole power minus 1. So that I write here. Similarly, I replace. What is this? The first derivative of the function at I. This is z minus z0. Z0 is I. Divide by 1 factor. Similarly, I write all the terms. Okay. See, in the exam at least you write 4 derivative. That is easy to convert the series into the summation form. Okay. Easily you can identify what series is. Okay. So that I am doing 4 derivatives and I am finding the 4 derivative values at the given z0 also. Okay. Then I replace it here. So now you see from the first term until the last one, what is here common? You can take as a common factor 1 minus I whole to the power minus 1 is a common factor. So I take it outside. So what is remaining here? 1. So plus here 1 minus I whole power minus 2 here. So I take minus 1. So what is remaining in the second term? So 1 minus I whole power minus 1 is remaining. But I write that remaining in the denominator, so that here 1 minus I whole power 1 will come. Understand what I am telling? So degree minus 2 is here. I've taken minus 1 outside. So what is remaining? 1 minus 1 is in the numerator. So I write down, that's why 1 minus I. Similarly, you do the remaining terms. So now what you will get? You see here 1 plus this is x plus x squared plus x cube plus x power 4, like that. So now what I can do, 1 over 1 minus I, this is multiply sigma n equals to infinity. Here this is nothing but x to the power n, because here you see all are positive here. So that, and here 1 plus this is in the general form 1 plus x squared plus x cube plus x power 4, like that. So what is the summation? That is sigma n equals to infinity x power n. We have seen in the first slide the rule. Okay. So x to the power n. So x is nothing but z minus I by 1 minus I. Okay. So that now here 1 minus I, here what is this actually? 1 minus I power 1 in the denominator. So now this and this you can join. If you make this, here the degree of this term is n. This is 1. So I write 1 minus I whole power n plus 1. Okay, so this is the given function in the summation form. Sigma n equal to 0 to infinity z minus I whole power n divided by 1 minus I whole power n plus 1. This is the Taylor series of the given function. Okay, that's it. Now you see the second question. Find Maclaurin series of f of z equal to e power minus z. Now you see, if the question is asked for Maclaurin series, here you don't expect z naught, because you have to assume that z naught is 0. Okay, that is the condition. What is Maclaurin series? So Maclaurin series is nothing but, in the Taylor series, you put this z naught is 0, then you will get Maclaurin series. So that, now see here, in the question it is not given what is z naught, but you can take z naught as 0. Okay, so now what you do, see f of that is e power minus z. So what you do, you find 4 derivatives. See, 1, 2, 3, 4. Actually here this is third derivative. Okay, here also it is third derivative. Okay, okay, so you find 4 derivatives and then you put z naught is equal to 0, which means here, see, for the function you put 0, means z 0, then you get 1. For first derivative you put 0, that is it. Okay, see, z equal to z naught is equal to 0. So now I find minus 1. What is the second derivative value? 1. Third derivative minus 4. Okay, so after finding these, see, you have to substitute in the series. Okay, now Maclaurin series we are going to find. That's why I put here 0, 0, 0 here. Okay, so now what will happen? You substitute here the function at 0. This is the derivative, first derivative at 0. Here z minus, this is the point 0, because Maclaurin series. Okay, so that similarly you write the next terms. Then what we can conclude that, see here, 1 minus z by 1 factorial, because here minus 1, so minus, next plus z squared by 2 factorial. Similarly you can write. Okay, see here, change in alternate term. Okay, sign change in alternate term, so that we can write, in the first slide we have explained that minus 1 power n z power n divided by n factorial. Okay, that is the sum of the series. Okay, sum of this series. Okay, so that f of z is equal to sigma n equal to 0 to infinity minus 1 power n z power n divided by n factorial. This is the Maclaurin series of the given function. That's it. Now we see what is the radius of convergence. See, this is a given power series. Okay, if mod z is less than r, then converges absolutely. Mod z is greater than r, then series is diverges. Okay, now this number r is called radius of convergence. We can see few examples for radius of convergence. Now you see here, find the radius of convergence of each of the power series. Okay, now this is the first one. Okay, so what we have to find, we have to find the radius of convergence. Okay, so as we know, we apply the ratio test. We know that. See here, limit n tends to infinity, cn plus 1 by cn. You can write an plus 1 by an or cn plus 1 by cn. Okay, this value is L. We know that, just you replace here. This is cn. So cn plus 1 means here n plus 1 squared z minus 3 power n plus 1 in the numerator. Then in the denominator you write cn. Okay, this term as it is. Then you simplify it. So what you are getting here finally? You see here, the limit is given for n tends to infinity. Okay, limit is given for n, but z minus 3. Now there is no limit for z minus 3. So you take this outside the limit. Now what is this? This is nothing but this will go to, see, 1. Limit n tends to infinity. If n goes to infinity here, then this value goes to 1, because this will be 0. Then 1 plus 0 is 1. Okay, so now you will get mod z minus 3, modulus of z minus 3. See what we get here, L is mod z minus 3. Okay, when the series converge, the series converge if L is less than 1. That's what we are writing. So what is L? Mod z minus 3. So mod z minus 3, if less than 1, then this is converge. Okay, so now therefore what is the radius? We know that, see, mod z minus 3 less than 1. So this is the radius. So what is the radius of convergence? That is 1. That's it. Now you see another question. See, in this question this is given cn. So you can write cn plus 1 cn, then you apply the limit. Now here similarly e modulus z plus I. After that you apply the limit n tends to infinity here. So you will get only this. So that we write L is equal to e modulus z plus I. If this is less than 1, then this will converge. Therefore, what is the radius? That is 1 by a. Thank you.